Hello guys, welcome back to Foolish Engineer YouTube channel. Today we are going to see a component without which any analog electronic circuit is incomplete. Have you ever seen those small triangular symbols in the circuit diagram? Yeah, those are called as OpAmps. And yes, we are going to talk about those in this video. So let's start. Well, what exactly is an op-amp? It's like that versatile ingredient which we use in different ways. Just like we use paneer in North Indian dishes. Like paneer butter masala, paneer tikka masala, kadai paneer, etc. etc. I miss North Indian food. We can use op-amp in different configurations just like that to amplify, compare and process signals. But first, let's understand the basics. The op-amp has two input terminals which are called as inverting and non-inverting terminals. And it has one output. It has two supply rails for positive and negative. It is made up of differential amplifier, gain stage and a push-pull emitter follow circuit at the output. It has this simple functionality. It amplifies the difference between two input voltages and produces the output that is usually much higher than this difference. This output voltage is in the multiplication factor with input voltage, and this multiplication factor is called as gain. For example, let's say I have an op-amp. I'll try to make a circuit out of it. Its positive supply rail will be connected to the 10 volts, and its negative supply rail will be connected to the ground. We give, let's say, 1 volt input to the non-inverting terminal and provide the ground to the inverting terminal. Then there is a difference of 1 volts between them. Now it will try to amplify this output with infinite gain. Well, we know it is not possible in real life, but this amplifier has open loop gain in the range of hundreds of thousands. So if you give input volt as the 1 volt, then you will get 1000 volts at the output. Sorry, it's not possible. If you do that, then you defy the laws of physics and you'll have a greater mind than Einstein and Stephen Hawking. You are creating power out of thin air. Unfortunately, we cannot do that because the input supply is only 10 volts. So this output will be limited up to 10 volts. And now, if we provide the 1 volt at the inverting terminal and ground to the non-inverting terminal, then the output terminal's voltage will be equal to the negative supply voltage rail. So it will immediately become 0 volts. So when the non-inverting terminal is high, then you get the voltage which is equivalent to positive supply rail at the output. When the inverting terminal is high, then you will get the voltage which is equivalent to negative supply rail at the output. So if you see this circuit in another perspective, then it looks like a comparator, right? Well, for now, let's skip that process of thinking. In a perfect world, our op-amp would have infinite gain, infinite input impedance, zero output impedance, and has no offset voltage. It would be like a superhero defying the laws of physics. But
wake up to reality.
In the real world, op-amps have some limitations. But before going to that, we have to consider two important rules. First, current doesn't flow in or out of input pins of the op-amp. And second, op-amp tries to keep both inputs at the same level. Let's keep this in mind and see the characteristics of an op-amp. First is its open loop voltage gain, which for an ideal op-amp would be infinity. But in reality, its range is in hundreds of thousands. Second is the input impedance of the op-amp. From the rules which we saw, the current doesn't flow from the input pins, so we can say that the op-amp has an infinite resistance. But in real op-amps, some small amount of current flows to the input, so the op-amps have high input resistance, which is in the range of mega ohms. Next is the output impedance. The ideal op-amp has zero resistance, so that the maximum value of signal should be taken out. It can act as a perfect voltage source without any internal losses. Well, Real op-amps have to differ with that. The real op-amps have some resistance which is in the range of 70 or 100 ohms. Now is the bandwidth. The fantasy of amplifying any signal from DC to highest AC frequency without any losses. That's like having unlimited talent. But in reality, op-amps have their gain limited by the bandwidth. They have a frequency range where they provide good output response. This limit is known as gain bandwidth product. This is given on a particular frequency where the gain of an amplifier becomes unity or 1. Next is the sneaky offset voltage. As we know, the op-amp amplifies the voltage difference between two input terminals. If the difference between two input voltages is 0, then logically the output should be also 0, right? Well, in ideal op-amp it would be. But in real op-amps, there's a small output voltage due to the offset. It's like that extra spice in your favorite dish, which you didn't ask for. If this offset voltage is small and can be ignored in the circuit, then it's fine. But if it is high enough, which can affect the circuit results, then we can use the nulling circuit to eliminate this error, which is generally given in the datasheet of the component. Now let's talk about the common mode rejection ratio, or CMRR. Let's assume we are giving some differential input signals at the inverting and non-inverting terminals. And if we check the equivalent output, it would cancel out each other. But due to some noise sources, there might be a possibility where a skew can occur between these lines. Then if we check the equivalent output, we can see some overshoot. This overshoot is referred to as common mode noise, and ability to minimize or ignore this noise is known as common mode rejection ratio. Imagine our op-amp is a party house, where differential input signals are the life of the party. But sometimes unwanted guests like common mode noise show up and cause a commotion. Then this CMRR is a bouncer outside of the party club to reject this unwanted noise and keep the party going smoothly. This common mode rejection ratio is given by this formula, where AD is differential gain and ACM is common mode gain. For ideal op-amp, this is infinite, but for our real op-amps, this is usually some finite value in dBs. And last but not least, we have the slew rate. Let's assume we are providing a PWM signal at the output, and the frequency of the PWM is very high. So this slew rate helps us in this scenario. It is a quantity which measures how fast an op-amp can respond to changes in the input. If the op-amp has very less slew rate, then there will be very high delays in the output. Real op-amps have infinite slew rates, but in reality, they have finite rates. Well, there you have it. Op-amps, the paneer of analog circuits, with their quirks and limitations. This is the basics about op-amps and its characteristics. I hope you picked up something useful from this. Well, don't forget to subscribe, and I will catch you in the next such amazing video. Till then, stay hungry, stay foolish.